Alright, this is our introduction to electric potential. So electric potential is measured in volts. The symbol for electric potential is V. So V is the symbol for electric potential and the symbol for the unit. The idea is that positive charge naturally moves from a higher potential to a lower potential. So we can think of a gravity analogy here. So there are sort of two ways to think about a ball rolling down the hill. There is the force way, so that we could say the ball rolls down the hill because the force of gravity pulls it down the hill. But we could also think of it in terms of potential energy. So if we think of the ball here as being high potential energy, and down here we would have low potential energy, we can say that the ball naturally would go from high potential energy to low potential energy. We can sort of make that analogy with electric fields. So if you think of two charged sheets like we have here, in terms of the force analogy, we can think of electric field lines. So the electric field lines would be parallel here. They would point away from the positive and toward the negative. And so if you imagine putting a charge in there, a charge of plus Q, it would experience a force and it would move this way. So it would end up with a velocity in that direction. And we know the force on the charge would equal Q times the electric field. So you could say, well, the charge moves because there's an electrostatic force on it due to the electric field. But we could also think in terms of potential. So when we did that potential mapping lab a while ago, the group that had this arrangement found that the equipotential lines were the lines of equal potential were parallel to the charges here. So if we think of these dotted lines, and if I say that this is a potential of, say, 4 volts, then 3 volts, then 2 volts, 1 volt, and 0 volts, then what we could say is that, similar to the ball rolling down the hill, the charge here, the positive charge, wants to move from a high potential to the low potential. And since it has the opportunity to do that, it would also have a velocity as it goes downhill. And that velocity would be changing, of course. It would accelerate in both cases. And so that's the idea here. Now we also have negative charges. What happens if you put a negative charge in there? The force would be in the opposite direction, which means that negative charges naturally move from lower potential to higher potential. So this is different than gravity. There's nothing gravitationally that moves from low to high, but electric charges, we do that. So we have lots of rules. Our rules always are spoken of in terms of positive charge, and negative charges always do the opposite. Okay. You can also see here that the electric field lines point from high potential to low potential. So if you're given potential lines and they ask you to draw an electric field, you could draw them in there, and they would point from high to low. You can also see that these electric field lines would be perpendicular to the equipotential lines. So equipotential lines are perpendicular to electric field lines. So if we imagine a point charge, what the equipotential lines would look like. So I'm going to pick a positive Q. The electric field lines, we'll always draw with solid lines, would go out radially from a point charge. Since this is a positive charge, they would point away color here, I'll put on my equipotential lines. We'll usually do these as dotted lines. So the equipotential lines, if you imagine them, they have to be perpendicular to the electric field lines at every point. So you end up with a circle of equal potential. I'm going to call that V1. And we have another circle of equal potential over here, and I'm going to call that V2. And you'll notice here that because the electric field lines point from high potential to low potential, we could see that V1 would be greater than V2. So another example that we have, sometimes I've seen this like on AP problems or something like that, if they just give you some electric field lines, they don't show the charges that generate it, and that's not the important thing. We don't want to get off in the woods trying to identify that, but you might have like electric field lines that look like this, and they might ask you to draw some equipotential lines on there. So equipotential lines, again, if I draw these, I want them to be perpendicular to the electric field here. So that would be like an equipotential line. Another equipotential line here would look something like that. So I might call this one V1 and this one V2. And if we look at it, in this case, the way I've drawn it, V2 would be greater than V1. That's how we display differences in potential. Now, potential and work. So in our example that we had before, we had a charge moving through through a difference in potential, and so there's a force doing work on it, and just like in mechanics, work produces changes in energy. So we had the work energy theorem. Doing work and lifting something changes its potential energy, and so on. So if we imagine again the same setup that we had before, if we have the positive and the negative, so that we set up this nice electric field here. If I put a positive charge in here, it's going to move, which means that later it may end up over here. So plus Q over there, I'm going to call this the initial, and this the final. So if you look at this, it's going to accelerate, it's going to experience a force in there, it's going to accelerate, so it's going to change energy. And so we could say the Coulomb force or the electrostatic force does work on the charge. And that work is equal to the change in kinetic energy of the charge. That's the work energy theorem. I'm getting a little sloppy. I think we just use K instead of KE for kinetic energy, so hopefully I haven't confused anybody with that. Okay. So we've talked about electric potential, and there's electric potential energy. So a charge that's in an electric field has potential energy, and the potential energy of a charge in the field is equal to the amount of charge times the electric potential. So U is the electric potential energy That's going to be in joules, just like we always measure energy. Q is equal to charge. That's going to be measured in coulombs. And V is the potential. Measured in volts. Knowing the potential energy of an object at one point is something that's sort of useful, but really what we are really concerned with is changes in energy. So again, we can do the same thing. So we can think of the change in potential energy using delta for change in is equal to Q times the change in potential. So let me give you an example here. So let's say that we have set up our thing like we've done before. So we're going to set up our electric field with our two plates. And actually, I'm going to, erase that. Let's think of it in terms of we'll have positive and negative, and we'll set up our equipotential lines here. So 3 volts, 2 volts, 1 volt. And let's say that I have a proton. So that's going to be plus, and E stands for the elementary charge. So that's going to be the elementary charge, the charge on a proton or an electron, just the sign is different. So we're going to say we have something is plus E there, and later it ends up over here. Actually, hold on a second, I'm going to change that. I'm going to change that to this. So we'll have plus E there. This is going to be the initial. And here we will have the final position. So when I calculate this, the change in potential energy is equal to the charge on that, and that's the elementary charge, which means that's 1.6 times 10 to the negative 19th, and it's positive, and our change in potential, this would be 0 volts over here, by the way, would be 0 minus 3. So that's negative 4.8 times 10 to the negative 19th joules. That's the change in potential energy. Now, just like we've had before, we have the law of conservation of energy still applies. So we're going to that's going to change into something else, probably kinetic energy here. I think we'll see in the next screen a calculation based on that potential energy. Now, a little bit about the units here. 10 to the negative 19th joules is a pain in the neck to use if you're doing this a lot. So, excuse me, if you're doing this a lot. So we define a unit called the electron volt, and the electron volt is equal to 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So that's going to make everything much easier. So let's do a quick example. Okay, so let's say a proton is in a linear accelerator, travels through a potential difference of 1,000 volts. We want to know what is the change in potential energy of that proton. So that's Q times the delta V. So again, the charge on a proton is 1.6 times 10 to the negative 19th joules, coulombs, times 1,000 volts. I'm not going to worry about the sign on this. So that is equal to 1.6 times 10 to the negative 16th joules. Okay, if I wanted that in electron volts, I know that 1.6 times 10 to the negative 19th or negative 16th joules. I'm going to do factor label method here. I want joules down here, and I want electron volts up here, and I know 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So that is equal to 1,000 electron volts. It's a little more convenient to deal with that. If you're working in the particle physics world, sometimes you'll have mega electron volts, sometimes giga, and even tera sometimes, but it's still better than carrying around the whole 10 to the negative 16th type stuff all the time. Okay. Now, how fast is it going at the end of that? The whole idea was to accelerate the proton, so we're going to use conservation of energy. So the law of conservation of energy says if we lose 1,000 electron volts, or 1.6 times 10 to the negative 16th joules of potential energy, it has to change into something else. So the U changes into kinetic energy, and kinetic energy we know is equal to 1/2 mv squared, whether it's an electron or a car or a person or anything like that. When using this, though, we have to work in joules, so we have to use our energy is 1.6 times 10 to the negative 16th. That's going to be 1/2. If you look up the mass of a proton, that's another one that's in that back cover of your book. It's 1.67 times 10 to the negative 27th kilograms times v squared. And in the interest of time, v turns out to be 437,700 meters per second. Quite fast. To the point where we would probably have to start thinking about relativity, or at least check that. So the potential due to a point charge is given by a formula, Q. For a point charge Q, the formula is V is equal to K times Q over R. You'll notice it's R. It's similar to other ones that we've used, but it's only Q, and it's just R on the bottom, not R squared. So if you think about this, we'll do some calculations here in a second. So potential is a scalar quantity. What do we mean by scalar? Remember, that means no direction. So since it has no direction, we don't have to worry about any sort of vector math when we do this. So let's wrap it up here by calculating the electric potential 2 meters away from an object with a charge of 4 times 10 to the negative 9th coulombs. So our potential here is K Q over R. So we've got 9 times 10 to the 9th power times 4 times 10 to the negative 9th power, all that over 2. So these cancel, and you can see that we have 36 over 2, which is 18 volts. So at any point 2 meters from this, I'm going to have a potential of 18 volts. So if I think about an equipotential line here, it's going to be a circle around this point charge. That might be the worst circle I've ever drawn in my life. But we get the idea as we go around there. So this is V is equal to 18 volts. And you can see that it's 1 over R, so if I cut R in half, I'm going to have twice the voltage. So if I'm in here at 1 meter, I would be at 36 volts. And again, that would be circular. Well, that is a good start, and we will continue with this later in class.